Reversi is a strategy board game for two players played on an 8x8 board. The main goal for each player is to turn over the opponent's game pieces that are in a straight line. In this project, we implemented three AI methods to design the controllers: breadth first search, Monte Carlo tree search, and reinforcement learning. The first method we used is the breadth first search. In this game, the cost of every move can be considered as 1, which means that this is a uniform cost problem. Breadth first search is a complete algorithm, and it is optimal when the cost is uniform. Therefore, it was selected as our first agent. There are some challenges for this method. The first one is time limit. Breadth first search searches through each layer, and it takes a relatively long time for it to find the solution. Therefore, we can set a decision time limit to avoid the timeouts. The second challenge is that we need to consider the opponent's next action to make a reasonable move. However, opponent's action is not fixed. In order to make it deterministic, we can iterate through all the opponent's actions and identify the state with the maximum score. The third challenge is the corner cases. When the actions include the positions in the four corners of a board, it's better to take corner positions because they are more likely to turn over the game pieces of the opponents.
Here I will briefly describe why we use Monte Carlo tree search and the challenges encountered in the application of the algorithm. The basic MCTS algorithm is designed in the diagram. We use MCTS because it is common in multiplayer games. Secondly, it is more in line with the human mindset. And thirdly, it is also used in the famous AlphaGo. Here is a brief overview of two challenges. For a timeout problem, we can solve it by limiting the dips. But for the problem of poor performance in the early stages of the game, it seems to be a common problem has not been solved so far.
The third type of algorithm we used is approximate Q-learning. In this project, I found that the biggest challenge for approximate Q-learning is that it's difficult to decide the appropriate metrics about the dimension feature list to put into use. Because in Reversi game, a lot of factors should be taken into considerations for our agent to win. Therefore, I solved this problem by introducing three types of different dimension feature lists. Firstly, we use two-dimension feature lists, which consists of my agent score and opponent's agent score. We calculate the Q value for every possible next state, corresponding to executing specific actions. And we select the positions which have the best Q value. As we can see clearly in the video, the opponent places a piece and 6-3, and my agent places a piece and 6-2. Because we use two-dimension feature list, my agent will only execute action which can reach the highest number of scores in the next state. But clearly, we know that the best place should be here, the 0-7, which is a corner. So we know that the two-dimension feature list is not that reliable, but it's easier to put into use. The second one is the 6-dimension feature list. The components are shown here clearly. As we can see in the video, the opponent places a piece and 2-0, and my agent places a piece and 1 and 0-0 rather than the 6-2. If it chooses 6-2, my agent will have the highest scores compared with other possible states. In this case, it proves that the new feature list functions properly. It has the good combinations of features to help my agent to win. And the number of features is neither more nor less. The last one is the winning rate is still not quite desirable. And final one is the 8-dimension feature list. And the components are shown here clearly. As we can see in the video, the components places the piece and 2-6. And my agent places the piece and 5-4 rather than 1-6, because 1-6 is a sub-corner. In addition, the execution of 4-6, 0-3, 0-5 shows that my agent tries to induce the opponent to place pieces and positions where we can stand more chances of placing our pieces and corners. In this case, it proves that the new feature list functions properly. As for the future improvements, personally, I think the most important one is to combine the different algorithms together to improve the winning rate. That's possible. And the next one is to find the optimal hyperparameters, including alpha, gamma, and epsilon. Maybe still effective.